Hello! I'm going to talk to you today about nutation. This is my handy dandy picture right here representing a top that is spinning with an angular momentum omega about its body frame E3 axis, and also processing about the lab frame z-axis. And because it's processing about the z-axis, it means that phi, the second Euler angle, is changing. But also, an interesting thing is that theta, the angle at which the top is from the z-axis, is also changing. That's the first Euler angle. It oscillates between two values, actually. And those values I'll get to in a little bit, but let's talk about the energy for right now. T, the kinetic energy, is given by this equation right here. It's equal to 1/2 lambda 1 times phi dot squared sine squared theta plus theta dot squared plus 1/2 lambda 3 psi dot, which is the third Euler angle, plus phi dot cosine theta, all squared, where lambda 1 is equal to lambda 2 but not equal to lambda 3. And those are just the principal moments for a symmetric top, which I'm representing right here. And the potential energy is given by this: the mass times gravity times r cosine theta, where r is the position of the center of mass given by this equation right here. And the angular momentum formula is given by the inertia tensor times the angular velocity vector. So the total energy we know to be kinetic energy plus potential energy. And we know this relation right here of psi dot plus phi dot cosine theta equals L3 over lambda 3, where L3 is just the angular momentum about this E3 axis right here. And phi dot is equal to Lz, which is the angular momentum about the z-axis, minus L3 cosine theta over lambda 1 sine squared theta. And so if you have these two equations and this t equation, you can plug these two equations in for psi dot and phi dot in all of the places you see here. And you plug the t equation and the u equation into this total E energy formula, you get this long thing. So the total energy comes out to be 1/2 lambda 1 theta dot squared plus Lz minus L3 cosine theta all squared over 2 lambda 1 sine squared theta plus L3 squared over 2 lambda 3 plus mgr cosine theta. Well, these substitutions were just to get a formula for the total energy in terms of only theta. And neither of the other two Euler angles. And so this gives us a value for the effective potential energy. So you could write this total energy right here is equal to 1/2 lambda 1 theta dot squared plus effective potential energy. And by knowing effective potential energy with respect to theta and plotting versus theta, you get this figure, which is figure 10.11 in John R. Taylor's classical mechanics book, where if you also plot the total energy along this effective potential vertical axis, then you get where they cross at theta 1 and theta 2. So these are our two values for which theta oscillates about. And going back to this formula right here for phi dot, that's equal to LZ minus L3 cosine theta over lambda 1 sine squared theta. If the absolute value of LZ is greater than the absolute value of L3, phi dot will never change sign. And you can see that because there is this negative here. If LZ is less than L3, there's the possibility of being negative or positive, so phi dot does change sign. And so representing this motion in this figure 10.12, you get this where phi dot doesn't change sign, and it just goes either in the positive or negative direction as theta oscillates between theta 1 and theta 2. Or this figure that represents if phi dot does change. Then it goes in this sort of circular motion as it oscillates between theta 1 and theta 2. And so we can see this nutation as demonstrated by this gyroscope right here. So if we turn this on, you see that little, as it spins around, it has this nutation. Though it's dampened by friction, so I have to keep bumping it a little bit. But this little nozzle, or nose, moves in a circular motion. So that's representing that figure B, where phi dot changes sign, and it moves in a circular motion. No matter how I push it, it always seems to go in that circular sort of motion. And again, it's dampened by friction, so it stops a little bit. But if I turn it off and then turn it back on, you'll see it process and start to process. And mutate.